Very well. So we finished talking about the essentials of waves, the fact that as the waves meet with each other, whether they meet in phase or out of phase, you have constructive or destructive interference, and the fact that you have wavelengths and frequencies. We can start talking a little bit about what happens when you have waves traveling through space. All right, so you could think of a wave moving through space in the following manner. You have this cylindrical extensions that is kind of like permeate and keep moving outwardly more and more and more. You might actually have seen this every time you've gone to a swimming pool, jump in the pool, and you kind of see the waves moving up and down, but they propagate in this circular fashion, and they keep on growing and growing as they move outwardly. When you think about the waves in the manner in which I just described in the previous video, not only do you have the waves moving outwardly, creating these bigger rings, they also move upwards or downwards, right? So you have a region in which the wave comes up, a region in which it comes down, and there's a region where basically neither happens, where you are exactly at neutral level. This is what we call the node of the wave. There's two kinds of waves that I want you to be aware of. One of them, which we're going to exploit entirely in the context of quantum mechanics, which is light. But I want to mention sound as well, mostly because this is something that you will encounter in physics and other science courses. So I'll depict it here as well. Now, each one of these types of waves, the sound wave and the light wave, have specific speeds associated with them. The speed of sound is 340.29 meters per second, which is actually rather fast. But the speed of light is a lot faster, 2.998 times 10 to the 8. This is roughly a million times faster than the speed of sound. According to relativity, this is the uppermost speed that most particles can travel at before some funky business starts happening. All right, but the interesting thing about this, something that you might have actually heard in the past, has to do with the idea of thunderstorms. First of all, if you think about how long it takes for each one of these waves, a sound wave and a light wave, to travel 1 mile worth of distance, which is roughly 1.7 kilometers. And the 1.7 kilometers itself is 1700 meters. If you think about the amount of time it would take each one of these types of waves to actually travel through a mile worth of distance, what you would do is, in the case of sound, divide the 1700 meters, which is the distance, by the 340.29 meters per second, right? So you'll have the 340.9 on the bottom, the 1 second on top. The meters will cancel out, and you'll find out that this is, roughly speaking, 5 seconds worth of time. So this is telling you that to travel 1 mile, sound will actually require 5 seconds of time to make that happen. If you do the same calculation using the speed of light, so divide 1700 meters by the speed of light, 2.998 times 10 to the 8 meters, times 1 second, you'll find out that this takes only 5.7 microseconds, and this is faster than you can actually blink your eyes. So as far as we know, like if there's a light source a mile away, we will see it. To us, it will look like it just happened instantaneously. Okay, but it actually took 5.7 microseconds. But because we really can't see that as a difference in time to our eye perception, technically speaking, what this tells you is that the moment you see lightning, you see it right away. If it's a mile away, the moment it happens, you see it almost instantaneously. But the sound that the thunder makes takes 5 seconds to actually reach you. So this is where you might have actually been told that if you see lightning, you have to start counting. And once you hear the actual sound of the thunderstorm, you stop the counting and you divide that number, whatever it is, by 5. And this tells you roughly how miles away the actual lightning struck. And it's all based on the premise of the speed of sound and speed of light. So it's kind of cool. I like to point that out just because it's a nice little conversion. Now, for waves, another thing that I want to discuss, because this is kind of gonna create the setup for quantum mechanics. When we talk about waves, there's a very specific way in which waves are depicted mathematically. We have either sine waves or cosine waves, but within the wave, we have a multiplier in front of it, which is called the amplitude. And within the wave, within the sine or cosine wave, we have angle parameters. We have a theta and phi. And depending how you change these things, you affect the shape of the wave itself. Now, focusing on the amplitude first. The amplitude basically tells you how tall the wave is going to be. In essence, it tells you how far you have to go from crest to trough. And if you increase the amplitude, you're basically elongating how tall this wave is going to look like. All right, so this kind of tells you, in essence, the intensity of light. So we're thinking now about light. Increasing the amplitude from the classical view of physics means that you're going to increase the intensity of light, because you're going to have a lot more intensity for it, right? A lot more amplitude. And then the parameters inside the trigonometric function basically determine the frequency and wavelength of the wave. You change these values, you change the wavelength and the frequency itself, right? So you could actually stretch out the wave, or you could actually compress it. And this is dictated by mostly the value of phi itself. You might even remember doing these things in algebra 2 trig. All right, but this is the classical view. Change the amplitude, change the intensity of the light, change the angle parameters, you change the type of frequency of light that you're dealing with. All right, now this is where I want to kind of stop the video, because this is where we're going to start getting into quantum mechanics. But the thing to be pointed out is that from the point of view of classical physics, the higher the amplitude of the wave, the more intensity you have for the light source, which in essence means that you have a lot more energy, because more light means more energy. That's kind of what traditionally makes sense, because we're kind of used to that continuity in terms of energy. But as you'll find out, that idea breaks down once we get into the quantum level. Okay, so I'll see you in the next video.